Okay, so when we last left off, we were focusing on drawing valence bond pictures using both atomic orbitals and hybrid orbitals. So just as a refresher into the idea of drawing molecular orbital pictures, let's look at hydrogen cyanide, for example. So our basic Lewis structure for hydrogen cyanide looks something like this. Now, if we think a little bit about the bonding pattern for carbon and nitrogen, we can start to notice some really important trends and behavior for this nitrogen lone pair and this carbon-hydrogen bond. So, first and foremost, this carbon is forming 2 sigma bonds, 2 single bonds, as well as 2 pi bonds. The nitrogen is forming a total of 1 sigma bond and 2 pi bonds. So if we think about the orbital diagram for carbon, initially before hybridization, it looks like we would be able, looking at our pre-hybridization orbital diagram, we're capable of forming two bonds, 1 sigma and 1 pi. However, if we think about how our p orbitals are arranged geometrically, their energy and geometry is not optimized for bonding. Further, we don't have enough half-filled orbitals to accommodate the number of sigma and pi bonds that carbon is forming. So in order to generate an appropriate number of half-filled orbitals to form these sigma and pi bonds, carbon will undergo hybridization to the sp hybridization. What that means is we'll take an s orbital and a p orbital, and we're going to average their energy and geometry and shape to generate 2 hybrid orbitals. These sp orbitals are relatively low in energy because they have a large amount of low energy s character. So we generate our sp orbitals, and of course, as always, we still have 2 p orbitals left over from this hybridization process. Now, if we distribute our 4 electrons across these orbitals to maximize bonding, we now have 4 half-filled orbitals, and as we can see, we can form 2 sigma bonds using our hybrid orbitals, and we can form 2 pi bonds using our empty p orbitals. A similar process can be visualized for nitrogen. The only thing that's unique about nitrogen, and the thing that really makes nitrogen a little bit special in this case, is just like our previous discussions where we were dealing with something like ammonia, for example, the nitrogen has 1 extra electron, and as a consequence, after hybridization, we end up with a bonding arrangement. We end up with an orbital arrangement where one of our orbitals is full. It contains a lone pair rather than a half-filled orbital capable of forming bonds. So if we fill in our 5 electrons, we notice that, and I'll box it in a different color to make it very visible, one of our sp orbitals contains a lone pair. Okay, so now that we have our hybrid orbitals established, let's look at each of our different types of bonding patterns. So to form the sigma bond between carbon and hydrogen, well, carbon can contribute an sp orbital. Hydrogen contributes a 1s orbital. And then in turn, we generate a sigma bonding orbital. Remember, when we write out our sigma bonding molecular orbital, we label the 2 orbitals that we've used to form that bond and to generate that molecular bonding orbital. And Just like always, when we form a bonding orbital, we also generate an antibonding orbital, which is empty in this case. Okay, let's look at our other bonding patterns. Let's look at our other bonding patterns. So let's look at our carbon-nitrogen bond for a moment. So carbon is contributing an sp hybridized orbital. Nitrogen is contributing an sp hybridized orbital. The orbital for nitrogen is slightly lower in energy because nitrogen has a greater effective nuclear charge. Let me draw this a little bit closer. So just like always, we're going to form our sigma bonding and our anti-bonding orbital. This will be a sigma bond between a carbon sp and a nitrogen sp orbital. And because the orbitals used to form each of these bonds are different, these two sigma bonds will have drastically different energies. Now, more interestingly, at this point, we've so far been describing our sigma bonds. Let's start to describe our pi bonds. And for our pi bonds, there are two possible geometries. So in the first case, we're going to look at overlap of a p orbital, and let's look at a pz orbital just for reference, so that way we can contrast it. So carbon is going to contribute its 2p orbital. Nitrogen will also contribute its 2p orbital because nitrogen has an available p orbital to form pi bonds. They're going to overlap perpendicular to the bond axis, and we're going to generate a pi bond and a pi bonding molecular orbital between a carbon 2p and a nitrogen 2p orbital, and we'll also generate an antibonding orbital. Now, one thing that's really critical to note, and I'll draw this out again, our pi bonding orbital entails constructive interference, where we have two regions of the same phase overlapping. P orbitals are phased, and the pi bonding molecular orbital occurs when we have two p orbitals with regions containing the same phase overlapping constructively. The pi star occurs when we have two regions of opposite phase attempting to overlap. So this is what a pi star looks like. This is what the pi bonding orbital looks like. Now, one thing that's a little bit interesting about pi bonds is there are two different geometries. If we look at the exact same example, except this time we're looking at a px orbital, for example. Still, we have to form one more pi bond between carbon and nitrogen. However, the p orbitals that we use to form this pi bond have a different three-dimensional arrangement. Now, this doesn't impact our orbital energies. They're both p orbitals still. So we do generate a pi bond between a carbon 2p and a nitrogen 2p, and a pi star as well. My question to all of you is, what changes about this pi bond? If we're using p orbitals with a different three-dimensional orientation, what is going to happen to our pi bond? Will it have the same or different orientation in 3D space? If we just look at our orbitals. And as we've noted in the chat, yes, it will have a different orientation. As we notice, the first pi bond is quote unquote vertically aligned, while the second pi bond is aligned along the horizontal axis. So we have two different pi bonds, each with a different three-dimensional orientation. And this is important because the orientation of your pi bonds determines whether they're accessible to other pi bonds for orbital overlap. And we'll see what I mean when we talk about resonance. So let's now put this picture together. So let's draw each of our atoms. Okay, now let's draw out each of our hybrid orbitals. So these are our carbon sp orbitals. Now to form our first chemical bond, our carbon sp orbital is going to overlap with our hydrogen 1s orbital. And overall, this overlap will generate a sigma bonding orbital consisting of a carbon sp orbital and a hydrogen 1s orbital. For nitrogen, nitrogen has two sp orbitals, the first of which it will use for chemical bonding. I'm going to move this down and you'll see why in a moment, just because our pi bonds are going to start taking up some space. And our second sp orbital is going to be used to hold a lone pair. Now this is important because if we understand where our lone pairs are located, we can begin to understand the energy and reactivity of that lone pair. Okay, so now let's draw our pi bonds. So the first of which is going to occur on the vertical axis. Remember, p orbitals are phased. So we have our first pi bond between our carbon 2p and our nitrogen 2p orbital. And now we have another set of p orbitals that are capable of overlapping to form our second pi bond. The only distinction being that this time our p orbitals are on the horizontal axis. So our overlap occurs on the horizontal axis. So this is our second pi bond. As we notice, our two pi bonds are perpendicular to each other in three-dimensional space. This will be important later on. Now, as a takeaway from this discussion, first and foremost, we note that this carbon-hydrogen bond has slightly different bond length and bond strength depending on the hybridization of our bonding carbon atom. So hybridization is directly impacting the nature of bonds formed using those hybrid orbitals. Further, if we think a little bit about this lone pair energy, I'd like us to reflect and recall that if we think about nitrogen with an sp3 hybridization, so suppose we have an sp3 hybrid orbital, compare that to an sp2 hybrid orbital, and then finally we compare that to an sp hybrid orbital. As we notice, depending on our hybridization, our lone pair energy is different. So the key thing that I want you to note, and the key thing that we're doing in all of these exercises when we draw these valence bond pictures, is we are very quickly identifying where is this lone pair located and what is the relative energy of that lone pair as a result. And as we can clearly note, the sp hybridized nitrogen, we have a low energy orbital, and as a result, we have a relatively low energy lone pair. Does that idea make sense to everyone? Does this idea make sense to everyone? Any questions on this idea? So let's try to summarize what we've discussed so far. So depending on the number of electron groups, you can also think of this as the number of sigma bonds, the number of single bonds. We can figure out the hybridization for each of our central atoms and in turn assign bond angles. You'll be responsible for knowing each of these hybridizations, identifying the bond angles, and identifying the geometry that results from each hybridization. Now, let's focus and let's really drill down on MO theory, molecular orbital theory. Let's talk about how it works, and let's talk a little bit about how we can use molecular orbital pictures, which are slightly different than valence bond pictures, in order to begin to understand the bond lengths and strengths in our molecule. Okay, so in molecular orbital theory, we're applying the Schrodinger equation, which we use to describe and generate these orbital pictures. We're applying this to a molecule, and we're calculating, rather than atomic orbitals, we're calculating molecular orbitals. Yes, you also need to know the molecular geometries as well. And we'll talk about that momentarily. Now, in practice, the solutions are estimated for these molecular orbital diagrams. Now, the main distinction between valence bond and atomic orbital theory and molecular orbital theory is that in molecular orbital theory, electrons are belonging to the entire molecule rather than the individual atoms. So we can think of it as if we're delocalizing our electrons across the whole molecule. Now, one idea that we really need to reinforce here is this idea of how do orbitals interact. So there are two types of interaction. The first of which is known as constructive interaction, where we have overlap when our orbitals have the same phase. So an example of constructive interference occurs when we form our typical sigma bond, our typical single bond. So if we have two hydrogen 1s orbitals of the same phase, indicated by the same color, they can overlap productively and generate a sigma bonding molecular orbital. The alternative method of overlap occurs, or the alternative method of how orbitals can interact is known as destructive interference. And this occurs when we have two orbitals with opposite phase attempting to overlap. This in turn leads to destructive interference and generation of a node, a region with no electron density. So a classic example of this occurs if you have, for example, a 2p orbital. If we have two of our 2p orbitals and they happen to have opposite phases, we will generate our pi star orbital. So let's showcase that overlap. Let's showcase that attempted overlap. Allow me one moment to color in one portion. So if we attempt to overlap two orbitals with opposite phase, what we instead get is an antibonding interaction, where there is no sharing of electron density between our atoms. There is a node between our two atoms. And that's why we often denote our node with this vertical dashed line. Does everyone see in this pi star orbital how there's no electron density shared in the middle of our two atoms?
Yeah.
Perfect, perfect. So that's a key feature of destructive interference or an anti-bonding interaction. So if the orbitals have the same phase, they overlap constructively to generate a bonding orbital. If the orbitals have opposite phases, they overlap destructively, forming an antibonding orbital, denoted with a star. Okay. So just to reiterate this idea with a picture. So when wave functions combine destructively, an antibonding molecular orbital is formed. This can be designated as a sigma star or pi star. So most of the electron density is found away from our two nuclei. So in this antibonding molecular orbital, there is a node. There is a region of no electron density between our two atoms. And in general, there's a minimal amount of electron density shared between our two atoms. Now, if we wanted to form bonding interactions, when wave functions combine constructively, we generate a bonding molecular orbital. In this case, most of the electron density is shared between our two nuclei. Now, it's important to note that when we combine two orbitals and we overlap two orbitals, we generate both a bonding and an anti-bonding orbital. So if we were to look at a picture, for example, at our hydrogen-hydrogen bond, both of these orbitals are accessible and can be interacted with depending on what is reacting with hydrogen. So in our first case, let's draw out our first case. So we have our sigma bonding molecular orbital. And additionally, overlaid on that sigma bonding orbital, we also have our antibonding orbital. And the one thing I want you to remember about this antibonding orbital is that it sits at 100 degrees opposite to our chemical bond. Now this is important because if you have a reagent, many reagents can break sigma bonds or single bonds by attacking this sigma star antibonding orbital. A similar phenomena or behavior is also observed for reactions that make or break pi bonds, where we have an attack on the antibonding orbital, which in turn breaks and weakens our chemical bond. So the location and the presence of these antibonding orbitals is really important to begin to understand the geometry and patterns of reactivity. Is everyone comfortable with this idea of bonding and anti-bonding orbitals so far? Any questions on this example? So let's keep going now, and let's talk a little bit about where do we place our electrons? Well, first and foremost, electrons are placed first in the lower energy bonding molecular orbital. So in the case of hydrogen, our 2 electrons are distributed into our bonding molecular orbital first. Now, the one thing that's unique about p orbitals is that they can engage in both sigma and pi bonding. So here's an example of the sigma and the sigma star orbitals formed from component p orbitals. when we think about pi bonds, just like in our sigma bonding example, our p orbitals can overlap either constructively or destructively to generate a pi bond or a pi bonding molecular orbital or a pi star antibonding molecular orbital. As we have two sets of p orbitals with different orientations, we have two sets of pi and pi star molecular orbitals, each with a unique orientation in 3D space. Does this concept look familiar to everyone? We're just refreshing this before we build on it. Does this look familiar to everyone so far? Any questions on this idea? So we're laying the groundwork to start to be able to answer some substantive questions about the strength, length, and characteristic of bonds in our molecules. And we're going to use these ideas to further analyze structures. So that's why we're focusing so much on these two orbital theories. Okay. So, from the perspective of molecular orbital theory, we can visualize our molecule as a set of molecular orbitals. Now, what's really important to note from our p orbitals is that only one of the p orbitals can form a sigma bond. The two remaining p orbitals are available to overlap to form pi bonds. Now, part of the reason behind hybridization and part of the rules that governs orbital overlap to form chemical bonds is that the orbitals used for bonding must be relatively close in energy. Now we know, of course, the p orbitals are higher in energy than the s orbitals. And from these premises, what we can do is we can take our component atomic orbitals. So in this case, we're taking our atomic orbitals for each of our two atoms. In this case, we're looking at two nitrogen atoms. We'll take our atomic orbitals and we will overlap them and generate a series of molecular orbitals. You can also generate a molecular orbital diagram using hybrid orbitals, but it gets more complicated when you start to move away from just two atom structures. Okay, so in molecular orbital theory, we've taken our atomic orbitals, we've overlapped orbitals that are close in energy to form molecular orbitals, both bonding and antibonding. And by looking at how the electrons are distributed in our bonding and anti-bonding molecular orbitals, we can in turn begin to describe the bond length and strength for this specific chemical bond found in our molecule. So let's unpack these molecular orbital pictures. Just before we move on, have we seen this before in general chemistry? Just in the chat, can I get an idea?
Very, very briefly.
Okay, so don't worry, we'll be unpacking it. We actually already have a lot of the building blocks in place already. So we're going to unpack these molecular orbital pictures, and we'll talk about how we can interpret them to describe bond length and strength, as well as bond order, which is essentially the number of bonds shared between our atoms. Okay. Now, there's one thing that I have to talk about before we unpack these pictures, and that is this idea of orbital energy. Now, as you've been noticing, whenever I draw out even a hybrid orbital, I'm very careful to note my orbital energy. And in general, orbital energy decreases with increasing effective nuclear charge. So I draw my arrow up and to the right. Elements that are farther on the right and higher up on the periodic table have a greater effective nuclear charge. They're more readily able to stabilize an electron. And as a result, electrons in those orbitals, and as a result, the orbital energy itself is lower. So orbital energy decreases with increasing effective nuclear charge and electronegativity. So for example, if we compare carbon and nitrogen, if we compare a 2p orbital for carbon, would we expect, following this premise, the energy for a 2p orbital for nitrogen to be higher or lower in energy? Higher or lower in energy based on this rule?
Higher.
So following the premise that orbital energy decreases with
Lower.
Oh, yep, exactly right. So nitrogen's 2p orbital is slightly lower in energy. Now this is really important because this in turn impacts how the orbitals overlap, and it impacts the overall molecular orbital energy. Okay. So the key thing I want you to know, the same orbitals for different atoms will have different energies. And in general, orbital energy decreases for atoms as you move up a column and right across a period. Why? Well, just to refresh your general chemistry, the higher up you are in the periodic table, the closer your electron is to the nucleus. Further, the farther you move to the right on the periodic table, the more protons are found in the nucleus, and those can stabilize our negatively charged electrons. Does that concept make sense to everyone? Does this idea make sense to everyone?
Yes.
Perfect. Are there any questions in the chat before we start unpacking another example?
What does nuclear charge exactly mean in this case?
So effective, so in this case, we're not just describing overall nuclear charge, but effective nuclear charge. So overall nuclear charge, which is described by the symbol Z, is describing the number of protons, it's describing the total charge of the protons in our nucleus. So for example, if we have 3 protons, it would be Z is equal to 3. Effective nuclear charge is a measure not just of the number of protons, but for example, if we look at our electrons, I'm drawing some inner shell and then our outer shell electrons, effective nuclear charge is describing how this outer electron interacts with our nucleus and accounting for shielding effects, repulsive interactions with our inner shell electrons. So effective nuclear charge is a measure of how much of the nuclear charge does our outermost electron, and by a result, the outermost orbital, interact with the nucleus. How much nuclear charge does that outermost electron and outermost orbital experience, accounting for all of the attractive and repulsive interactions? Does that answer your question?
Yeah, will we be going over that more later on, or is that kind of just what we need to know?
So the main thing that I want you to know for effective nuclear charge, and we've sort of summarized it in this rule below, is that effective nuclear charge increases as you move up and to the right on the periodic table.
Oh, okay.
Effective nuclear charge is very closely correlated with electronegativity as one measure. And it serves as a proxy to describe how readily is, or how effectively is that outermost electron, that outermost orbital, stabilized by the nucleus of our atom. And because each atom has a different number of protons, in their nucleus and a different number of shielding electrons, the effective nuclear charge is different, and in turn, the orbital energy is slightly different. Does that make sense?
Yeah.
Perfect. We will actually, we'll talk a little bit more about this when we start to look, and we actually see this trend when we start to change our orbital size, because the larger our orbital gets, we're not only getting farther from the nucleus, but our effective nuclear charge also decreases a little bit because we're adding some inner electrons that are shielding. And as a result, our outermost electron for a larger orbital experiences overall less of our nuclear charge. Does that make sense? Does that tie it back to a concept that we've seen before?
Yeah.
Perfect, perfect. So with this knowledge in mind, with our knowledge in mind for looking at relative orbital energy, if we look at the atomic orbitals for nitrogen and oxygen, as we notice, oxygen is farther to the right on the periodic table, has a greater effective nuclear charge, it's more electronegative, so its outermost orbital energies are lower. This in turn impacts the energy of our bonding and our antibonding orbitals. And in turn, it directly influences the arrangement and the relative arrangement of our sigma and pi bonding orbitals in our molecular orbital picture. Okay, so you need to pay attention to the atoms used for bonding because it directly impacts the relative energy of our sigma and pi bonding orbitals. Okay, we'll unpack this picture in more detail momentarily. Now, there are a few terms that we need to know. The highest unoccupied molecular orbital, otherwise known as the HOMO orbital, is the highest energy orbital containing electrons. It's the highest occupied molecular orbital. The lowest unoccupied molecular orbital, otherwise known as the LUMO orbital, is the lowest energy orbital that does not contain electrons. Chemical reactions typically involve interactions with a molecule's HOMO and LUMO orbitals. Okay, so to tie this back, if we're looking at our picture.
Is that how they attack the antibonding you were explaining earlier?
Yes, although this is a little bit different in that bonding and antibonding are invoked in valence bond theory to describe a specific antibonding orbital for a specific bond in our molecule, while the HOMO and LUMO molecular orbitals, they can be attacked and occupied, similar to a bonding and antibonding orbital, but the HOMO and LUMO are describing the electrons throughout our molecule or throughout a large set of atoms. And the best, let's first label the HOMO and LUMO, and then we'll talk about cases where the HOMO and LUMO orbitals are utilized to describe chemical bonding and other reaction processes. So for example, in this molecular orbital picture, our LUMO would be our sigma star, and our highest occupied molecular orbital will be our pi star. Now, when we're looking at different molecular orbitals, and just to help you visualize the importance, this is a little bit ahead of what we're going to be talking about, but I'll discuss this just so you can get a sense of why this is important. So We're describing molecular orbitals, which describe the distribution of electron density and any nodes present in our structure throughout a large set of atoms. Okay, so if we were looking, for example, at the LUMO and HOMO for a pi system, or a collection of electrons spread across pi bonds in multiple atoms, we can actually draw a picture that describes the LUMO and HOMO molecular orbitals, the distribution of electron density, and the orbitals that are used to describe the distribution of electron density in our molecule across multiple atoms. And what we do in these models is, by drawing out our HOMO and LUMO, orbitals, depending on the distribution of electrons and depending on the state of our molecule, whether it's in a relaxed or excited state, either the HOMO or the LUMO orbital will be describing the chemical bonding arrangement in our molecule. So for certain chemical reactions, for example, they can be driven by heat. In this case, the phasing and the distribution of electrons described in our HOMO orbital can tell us and can inform how this molecule will undergo chemical reactions. So essentially, the HOMO and LUMO molecular orbitals describe the distribution of electron density in our molecule. And in turn, just like we can study the interactions between atomic orbitals, we can study the interaction between molecular orbitals of different molecules to understand bonding processes. So that's a complicated way to say the HOMO and LUMO, yes, they're accessible. Yes, they can be attacked. Yes, they can be filled with electrons, just like a typical bonding and antibonding orbital. But they're instead describing the electron density in our entire molecule. Does that answer your question? I know it was a bit of a long-winded answer, but does that distinction make sense between just a normal bonding and antibonding orbital versus a molecular orbital?
Yes.
So just the shortest explanation is that bonding and antibonding orbitals look at the bonding arrangement for a set of atoms, while molecular orbitals look at the bonding arrangement for the entire, or the arrangement of electrons and what orbitals those electrons are located for our entire molecule. That's why it has the name molecular orbital, because it's trying to describe our entire molecule.
Okay, and then just one last thing too. On this this picture here, and it's showing the 2p for nitrogen is higher than the 2p for oxygen.
Yes.
Is that intentional based off of what you were explaining earlier about the difference of energy?
Yes, exactly right. Oxygen is more electronegative. It has a larger effective nuclear charge, and as a result, it has a lower orbital energy for its atomic orbitals.
Okay, so then we would just have to draw, whichever one is typically lower, you just draw it lower.
Yes, exactly right. Because that directly impacts our bonding and antibonding orbital energy. Does that make sense?
Yep.
Perfect. Okay. So when we think about bonding and antibonding orbitals, we can actually look at how many electrons are occupying our bonding and antibonding orbitals to begin to start to describe the bond strength and bond length found for the bonds in our molecule. So electrons in bonding molecular orbitals are low in energy. Electrons in antibonding molecular orbitals are high in energy. So electrons in antibonding orbitals will cancel the stability gained by electrons in bonding orbitals. In other words, filling a bonding molecular orbital strengthens the bond. Filling an antibonding molecular orbital weakens and can break your bond. So we measure the relative bond strength using this idea of bond order. So as bond order increases, the bond becomes stronger and shorter. Now, bond order is described as the number of bonding electrons, those in our sigma and pi bonding orbitals, minus the non-bonding electrons. Well, let's be a little bit more precise here. And I prefer for you to think of it not just as non-bonding, but the anti-bonding electrons, the sigma star and pi star orbital electrons. So if the bond order is equal to 0, there's no bond and the molecule is likely not stable enough to exist. Now, there are two more terms that we often invoke and we discuss when we talk about these molecular orbital pictures. The first of which is this idea of paramagnetic and diamagnetic. So a substance is considered paramagnetic if its molecular orbital diagram has an unpaired electron. If all electrons are paired, it's known as a diamagnetic molecule. So looking at nitrogen monoxide, we can in turn calculate the bond order. So in this case, the bond order, first and foremost, we count up all of our bonding orbital electrons. So for our bond order, we have 8 bonding electrons, and then we subtract our anti-bonding electrons, which would be 3 divided by 2, and that in turn gives us a bond order of 2.5. So what does this tell us practically? Well, it gives us a sense that the bond order for this nitrogen-oxygen bond is not quite a double bond and it's not quite a triple bond. It's intermediate between a double and triple bond. Further, there are a few other things to note here. When we fully fill an antibonding orbital, those electrons, rather than being shared in a chemical bond, will instead be localized as a lone pair on one of our atoms. Now, what's really interesting here is because we have one electron in our antibonding orbital, we have what's known as a radical, where rather than a pair of electrons being localized on our atoms, we instead have a single unpaired electron. So when you end up with these bond orders that don't match a whole number, it's often very tricky for your Lewis structure. So this is an 11 electron Lewis structure. It's very hard for your Lewis structure to accurately describe the chemical bonding pattern in your molecule. And that's because for these intermediate bond orders, we don't have quite a double bond. We have a bond that's stronger than your typical double bond, but weaker than your typical single bond. We can describe the structure with these dotted or dashed lines, but the main strength of molecular orbital theory is it can describe bonding arrangements that Lewis structures often have difficulty accurately and precisely describing. Does everyone understand this bond order calculation? And does everyone understand how this plays into this idea that we don't have quite a triple bond, but we have something that's stronger than a double bond? Does that part make sense to everyone? Any questions on that idea? Does it make sense how we calculated this bond order?
Could you just show how you got 8 minus 3 one more time?
Yes. So counting our bonding electrons, we have 2, 4, 6, 8, because these are the total number of electrons in our bonding orbitals. And then for our antibonding electrons, we have 2, 3. So we subtract our bonding electrons minus our antibonding electrons, and then we divide by 2. That gives us 2.5.
Okay.
Does that make sense?
Yeah.
Perfect. Yes, did you have a question?
Yeah, sorry. I just honestly, I kind of forget the order of filling out one of these diagrams again. Like,
Yeah, we'll talk about that actually, because
okay.
the filling order actually depends on what atoms are used to form the bond.
Okay, thank you.
Yeah. So we'll talk about that in a second. The other thing that I'd like everyone to note, does everyone see that unpaired electron? We have this unpaired single electron. So this is a key sign that we have a paramagnetic molecule, a molecule that is affected and is attracted to an external magnetic field. And the fact that it's a single unpaired electron, and we have a single unpaired electron in our antibonding orbital, this single unpaired electron indicates and can help explain why we observe a radical in our Lewis structure, why we observe radical-like behavior, where we have a single unpaired electron. Okay, so molecular orbital diagrams and Lewis structures are trying to describe the bonding arrangement and the arrangement of electrons in our molecule. Molecular orbital pictures can give us a more exact picture of the bonding arrangement in our molecule, and really can help supplement Lewis structures when we start to look at bonding arrangements for more complicated examples. Does this idea make sense to everyone? So we're already beginning to use these pictures to describe our bond length and strength. So we're making some progress here. Okay. So in terms of our filling order, we'll talk about that a little bit later on. The main idea I just wanted to impress on you for now is this idea of how we can calculate our bond order by looking at our bonding and antibonding electrons, and this idea that filling the antibonding orbital breaks our chemical bond. Okay, so we're now going to take a little step back here. We're going to take a step back here, and now we're next going to look and see, well, we have these rough models of how to describe bonding and how to describe the distribution of electrons in our molecule, let's talk a little bit about how we can describe the geometry and shape of our molecules. And to do that, we're gonna review and discuss VSEPR theory, which is an overall theory used to describe the geometry and shape of molecules. So first and foremost, in VSEPR theory, we describe bonds as electron pairs. In VSEPR theory, lone pairs and electrons will repel each other. And the central tenet of VSEPR theory is this idea that electrons and bonds and lone pairs are arranged to minimize electron-electron repulsion. Thus, our geometry depends on the number of atoms bonded to the central atom and the number of lone pairs. We call these charge spheres. Now, an electron group or charge sphere is defined as a single lone pair of electrons or a bonded atom. So a bonded atom is one electron group, regardless if it's single, double, or triple bonded. That makes sense so far. We can use the steric number, which is the total number of electron groups, in other words, the number of bonded atoms plus the number of lone pairs, and we can in turn determine the electron pair geometry. Okay. We've done this before, we've seen this before, and we've discussed electron pair geometries earlier on in this chapter. Now what we're going to do is we're going to look at some of our electron pair geometries once again, and then we're going to see what happens when we start to introduce lone pairs and we start to observe the effect of repulsions on our overall geometry. So, just as a refresher, the linear electron pair geometry, so we're looking at electron pair geometries. We have two sources of electron density or charge spheres, and we have 180-degree bond angles. Again, we don't count double and single bonds differently. We're in essence just looking at the total number of sigma bonds in order to get a sense of the electron pair geometry. Now we've seen this before. This is not particularly exciting. Just continuing our review, the trigonal planar geometry has three sources of electron density or charged spheres, and it has 120-degree bond angles. Wonderful. The tetrahedral geometry has four charged spheres, and it has a three-dimensional shape associated with it, and we have 109.5-degree bond angles. Okay, so these are each of our electron pair geometries. And what I want us to do now is to just review briefly the electron pair geometry for each of these example cases. So we'll look at each of these examples. I'll do the first one and you'll do the second one just as a refresher. And then what we'll do is we'll look and see what happens when we start to change the number of lone pairs associated with these structures. So let's start by just making sure we still know our electron pair configurations. So for aluminum chloride, we have a total of 24 electrons. We place aluminum in the center and we form one bond each. Then we add our lone pair electrons, and that in turn gives us 24 electrons. Now, if we think about our total number of bonds and lone pairs on our central atom, we see that aluminum has 3 sigma bonds and 3 charged spheres. And as a result, we can conclude it would have the trigonal planar geometry. So if we're drawing aluminum chloride respecting its three-dimensional shape, aluminum chloride would be completely flat and we would have bond angles of 120 degrees. So I'd like you now to review and to draw out the Lewis structure for chloroform. And I'd like you to tell me the electron pair geometry, and I'd like you to attempt to draw a three-dimensional picture for carbon tetrachloride that accurately reflects its bond angles. So I'll give everyone about 2 to 3 minutes, and I'd like you to respond in the chat with the proposed electron pair geometry for chloroform. And if you have any questions when working through these examples, don't be shy to ask your question verbally or to ask your question in the chat. What we're doing here is we're setting the baseline, so making sure that we're familiar with the electron pair geometries so we can build on it and start to describe the molecular geometries. So let's spend about 2 to 3 minutes on this example, and then we'll discuss shortly. And let's try to get a few more responses in the chat, and then we'll discuss. Let's spend about another minute on this example. Let's try to get a few more responses in the chat for the proposed electron pair geometry for chloroform, and then we'll discuss shortly. Okay, so let's discuss this example. So adding up our electrons, we have 26 electrons to work with. We put carbon as our central atom and we surround it with our 4 chlorines. Then we add in our lone pairs.
Wasn't it 3 chlorines?
Ah, yeah, sorry about that. I'm thinking of carbon tetrachloride. Sorry, 3 chlorines and our 1 hydrogen. We've used up all of our electrons. And now looking for our electron pair geometry, we have 4 sigma bonds and 4 charged spheres. And that in turn tells us we have what electron pair geometry? 4 charged spheres, what electron pair geometry does that match?
Tetrahedral?
Tetrahedral, exactly right. So then, when we draw our three-dimensional picture for chloroform, we're going to need to respect the fact that this molecule has three-dimensional shape. And we need to respect the fact that the bond angles in this molecule are 109.5 degrees. Now, you can also describe three-dimensional shape using dash wedge notation, where the wedge indicates it's pointing towards you, the dash indicates it's pointing away, indicates the atom is pointing away from you. Both methods are valid. I want everyone, when you draw your Lewis structures, to be especially attentive towards making sure your Lewis structure is accurately reflecting the bond angles and the shape around our central atom. Okay, perfect. So now we have this base to build off of. And let's talk about the relationship between electron pair and molecular geometry. So the electron pair geometry is the geometry based on the number of charge spheres. The molecular geometry, which is what we're interested in, is the geometry accounting for lone pair and bonding electron repulsions. Molecular geometry depends on the electron pair geometry and the number of electron lone pairs on our central atom. Now, to explain why this is, we need to sort of think about lone pair electrons. And what we notice is that electron lone pairs take up more space due to repulsive interactions between the lone pair electrons. These two electrons are repelling each other, and that in turn means our lone pair is taking up a lot more space and can engage in a lot more repulsive interactions with our adjacent bonds. Now, why does this matter? Well, electron lone pairs repel bonding electrons, leading to a smaller distorted bond angle. That's why if we look at something like ammonia, for example, NH3, in other words, described, if we were drawing out its structure, it would look something like this. Repulsions between this lone pair and our bonding electrons in turn compresses our bond angles. Our bonds are pushed closer together to get away from this lone pair, and in turn, our bond angle is now distorted by about 1.5 degrees. In general, lone pairs lead to smaller bond angles relative to our baseline electron pair geometry. Does this idea make sense to everyone? Have we seen this idea before?
Yeah.
Perfect. Okay, so now what we're going to do is we're going to do a brief survey of all the relevant molecular geometries, starting with our tetrahedral variants. So what makes a molecule trigonal pyramidal? We have 4 charged spheres and a tetrahedral electron pair geometry, but this time we have 1 lone pair. That in turn leads to a 107.5 degree bond angle and a trigonal pyramidal molecular geometry. The next tetrahedral variant is the bent variant. The bent variant has 4 charged spheres, and this time we have 2 lone pairs. This in turn leads to a 105.5 degree bond angle. Now there's some variance in the textbooks. How much does a lone pair actually affect the bond angle? It's between 104.5 and 105.5. Depending on your textbook and depending on your instructor, the exact value for this geometry will be a little bit different. That's because different molecules have slightly different bond angles as well. do these two geometries make sense so far? Does this look familiar to everyone so far?
Yep.
Perfect. So now we're going to look at the trigonal planar variants, and the variant that we need to discuss is the bent trigonal planar variant. This time we have 3 charged spheres, so we have a trigonal planar electron pair geometry, but this time we have 1 lone pair. This lone pair in turn compresses our bond angle to a bond angle of 116 degrees. Now, I'm not expecting you to memorize every single bond angle. What I do expect you to know, and what I do expect you to be familiar with, is that the lone pairs reduce our bond angle, and for tetrahedral geometries, it's about 1.5 degrees per lone pair. For trigonal planar geometries, it's about 4 degrees. So here's a table summarizing electron pair and molecular geometry for many of the common molecules that and common geometries that we see in organic chemistry. You should be familiar with this list, and you should be comfortable assigning electron pair and molecular geometry, in addition to hybridization.
Sorry, you said it's not extremely important to memorize the actual bond angles, just to understand the fact that lone pairs.
Yeah, just the fact that it's less.
Okay, and you said about 1.5.
Yes. So for the tetrahedral electron pair geometries, for each lone pair, it translates to roughly a 1.5 degree reduction, while for the trigonal planar, each lone pair results in about a 4 degree reduction. Just as a rule of thumb.
Cool, thank you.
Yep, perfect, perfect. Okay, so things are best learned via practice. So what we're going to do now is we're going to look at the formula. We're going to try drawing out the Lewis structure, and then we're going to identify the molecular geometry for each atom. So let's look at this molecule, CH2CO. This one's pretty interesting, and I'll start us off with this first example. So first, first for counting electrons, we have 4 times 2 for carbon, 1 times 2 for hydrogen, and 6 for oxygen. So we have 16 electrons to work with. We're going to in turn write both of our carbons as central atoms. We're going to surround our leftmost carbon with 2 hydrogens following our formula, and the rightmost carbon with an oxygen. We're then going to form 1 bond each, 2, 4, 6, 8. We have 8 electrons remaining. Now we're going to add our lone pairs. Then what we're going to do let me just double check that we've added this up right. CH2CO, so we have 8, 10, 16, 2, 4, 6, 8. We have 2 electrons remaining. We place our last 2 electrons on carbon. Now, in order to fulfill the octet of our central carbon, we're going to convert our lone pairs into bonds. And that in turn gives us the following valid Lewis structure. Now, we have to assign the molecular geometry for each of our central atoms. So I'm going to label this carbon 1 and carbon 2. So for carbon 1, as we have a total of 3 charged spheres and no lone pairs, it would have a geometry of trigonal planar. Carbon number 2, as it has 2 sigma bonds, 1, 2, it would have a linear geometry. So then, if I'm drawing this molecule respecting the bond angles, I would have a 180-degree bond angle on our central atom. And then I would have 120-degree bond angles for our second carbon atom. Notice how when I'm drawing my bonds, I'm arranging my bonds so the position of my bonds matches my bond angle. Does that make sense to everyone? So your drawings should reflect the geometry. So what I want everyone to do now is I'd like you to take a look at the following two molecules, and this will be our last exercise for today. I'd like you to assign the geometry for each of our central atoms in these structures. Each of these structures have 2 to 3 central atoms. And then once you've assigned the geometry for each of your central atoms after drawing your Lewis structure, I'd then like you to draw a 3-dimensional accurate drawing of your molecule. You want to start to be able to visualize molecules in 3-dimensional space. So we'll give everyone about 6 minutes to work on this assignment, and then we'll come together as a group to discuss. Don't be shy to share your proposed geometry assignments in the chat, or to use the annotate feature and share your proposed Lewis structure. And we'll discuss this example momentarily. And if you have any questions when working through this example, don't be shy to ask it in the chat. And if you're comfortable using the annotate feature, you're more than welcome to share your proposed responses using the Zoom annotate feature. I want to make sure everyone is comfortable not only drawing Lewis structures, but assigning geometries from those Lewis structures. And I would double for when assigning geometries, make sure you're counting the number of sigma bonds rather than the total number of bonds. And we'll continue working through this example and we'll discuss momentarily. Let's try to get a few more responses in the chat for the proposed molecular geometry for each of our central atoms. And then we'll discuss this example in about another 2 to 3 minutes. And the responses I'm seeing in the chat look great so far. So just to tie up today's session, let's look at acetic acid. So using our bonding shortcuts that we've learned earlier on in this chapter for bonding preferences and our descriptive formula. So for CH3, I'm going to draw a carbon with 3 hydrogens. For our CO2H functionality or carboxylic acid functionality, I'm going to draw my carbon attached to my 2 oxygens, and attached to my oxygen, I'll add a hydrogen. So this is the rough Lewis structure for acetic acid. I'm now going to label my carbons 1, 2, and I'm also going to look at the oxygen as number 3. So for carbon number 1, I have 4 sigma bonds. So this is tetrahedral. For carbon number 2, I have 3 sigma bonds. So this would be trigonal planar. And for oxygen number 3, I have a total of 1, 2 bonds and 2 lone pairs. So that oxygen would adopt the bent geometry. So if I'm drawing this molecule with respect to its 3-dimensional shape, I make sure my bond angles, around my central carbon are 120 degrees. I make sure to reflect my bond angles around my oxygen are about 105.5 degrees. And then for my carbon, I need to make sure that I'm accurately representing the fact that this carbon has 3-dimensional shape and a bond angle of 109.5 degrees. Does this make sense to everyone so far? So just to show everyone a picture of what this would look like. So here is a molecular model of acetic acid. And just to help you really clearly see, the central carbon is flat. The methyl carbon or the CH3 group carbon has 3-dimensional shape. And this will be very important later on in later chapters. So to continue on and just to round out our examples, does anyone recognize this molecule by chance? Any biology majors want to chime in with, does anyone recognize this molecule? Would anyone like to state the name for this molecule? I'll give you a hint. You've seen it. Yes, urea, exactly right. So for people who say, oh, this isn't biologically relevant, we're looking at all sorts of molecules that pop up a lot in your biochemistry and biology textbooks. So drawing out our Lewis structure from our different functional groups. We end up with a structure that looks something like this. Now, looking at each of our nitrogens, so for our nitrogen geometry, we have 3 bonds and 1 lone pair. So that in turn gives us not trigonal planar, but trigonal pyramidal geometry. For our central carbon, we have 3 bonds. So that in turn gives us a trigonal planar geometry. So if we are drawing out urea with respect to its bond angles, we would note that our nitrogens have 3-dimensional shape around the central atom. And our bond angles are about 107.5 degrees. For our central carbon, our bond angles are about 120 degrees. Now, this is great in practice, but what I want us to think about, and just as a teaser for the next lecture session, in reality, if we actually look at urea and we look at each of these nitrogens, the geometry of each of these nitrogens in urea, when we look at crystal structures of urea, this geometry actually adopts a trigonal planar like geometry. And our goal for next class session is to explain why this is. Does anyone have a guess? Does anyone have a guess? And this would be a great prompt if you want to structure your reading. Let's try to get some guesses in the chat before we close out today's session. Would anyone like to take a guess? So we have a few responses in the chat. I'd encourage you to read through chapter 1 and 2 of your text. And what we're going to do next class session, just so that way you have a little bit of suspense and interest in sort of thinking about this over the next few days before we start our next class session, is to try to think, why are we seeing a trigonal planar geometry in our actual structure? And as a hint, the answer lies in the resonance effects on our bond length, strength, and arrangement of electrons. So we'll pause our lecture here